Hello everyone, my name is Amir Hossein and I will be presenting a new variant of the bakery algorithm called Bakery++. This algorithm avoids register overflows. First, I will give a background on the problem of mutual exclusion and the bakery algorithm itself. Then I will state the problem that we are trying to solve, and after that, we shall see how the Bakery++ algorithm works. We will consider its performance, practicality, and correctness, and we will present two questions about the algorithm for future work. Mutual exclusion started the field of concurrency. It was proposed and solved by Dijkstra in 1965. A group of independent sequential processes that have access to shared memory. This problem is actually concerned with this group of processes. And the goal is to prevent these processes from executing a specific region of the code called the critical section at the same time or simultaneously. There are a number of correctness conditions specified by Donald Knuth for this problem. The first one is that no two processes are allowed to execute their critical sections at the same time. A reliable process should be allowed to enter its critical section eventually, meaning that it should not be blocked forever. Failure or crashing of a process should not block other processes from accessing a critical section. Processes are allowed to fail at any time and then restart outside of their critical section, and no assumptions are made about the execution speeds of processes, meaning that they are asynchronous. Resource management in computer systems is usually concerned with coordination and collaboration of users, and it is usually based on making a decision. In the case of mutual exclusion, that decision is about granting access to a resource. This resource may be executing a specific region of the code that is the critical section. Mutual exclusion, therefore, is useful for supporting resource access management. The bakery algorithm has a number of properties. The first of them is that processes can enter their critical sections in first-come, first-served order, and the failure of an individual system component will not cause the entire system to halt. One of the two remarkable properties of the bakery algorithm is that no process writes into the memory location of other processes. The second remarkable property is that if a read and a write operation occur at the same time for a specific memory location, then the value obtained by the read operation may have any arbitrary value. This is the original bakery algorithm. As you can see, the process I will choose a numbered ticket that is larger than all other existing numbers in the system. Then it will wait until the conditions are met, and after that it can execute its critical section and reset its number, and then restart again. There is a problem with the bakery algorithm, and the problem is that it assumes unbounded registers. Every process I has a variable called number, and it may tend to infinity in the original bakery algorithm. Two competing processes may keep incrementing the value for number I forever, because they will read the values of other processes and they will increment it by 1. This will cause register overflows in real systems. Of course, it is not a problem of the algorithm itself, because algorithm is an abstract, not a real implementation, not a real system. And in algorithms, you can assume integers that may tend to infinity, and that is no problem. But in real systems, it will become a problem, because registers can store bounded values. Our purpose is to avoid register overflows in the bakery algorithm without making compromises like other solutions have done. Previous approaches to achieve the same goal include introducing new shared variables, or redefining certain operations or functions in the original bakery algorithm. Our goal is to solve the problem without making compromises, without introducing new shared variables, or without redefining operations or functions of the bakery algorithm. Notable solutions that have tried to solve this problem, they have taken certain measures in solving the problem, which include changing the definitions of less than operator and maximum function in the algorithm, or using modulo arithmetic instead of integer arithmetic, or they have introduced new shared variables or used extra memory, or they have reset the values of the registers before an overflow occurs. Our solution is quite similar to the fourth approach here, but our algorithm, Bakery++, is much more simple than any other previous algorithm that solves the same problem. There is an important theoretical question in the algorithm in the paper that introduced the bakery algorithm. Can one find an algorithm for finite processors such that processors enter their critical sections on a first-come, first-served basis, and no processor may write into another processor's memory? To the best of our knowledge, all previous works on bounding the bakery algorithm have failed to answer this question, because they have either used quite complicated solutions, or they have allowed processes to write into each other's memory locations. Bakery++ is a slightly modified version of the bakery algorithm. We call it Bakery++ because it is almost identical to bakery. It does not use additional variables, and it does not redefine the operations or functions used in bakery itself. This is how the Bakery++ algorithm works. As you can see, it is almost identical to bakery itself. The first change is that we have declared a constant m that represents the maximum value that can be stored in a register. At the beginning, we will check if there exists any number in the system that is larger than or equal to the value of m. If there is, then we will go to L1 again. This means that we are waiting here. What are we waiting for? We are waiting for the process owning that variable number q to reset its number to 0. As you can see, at the end of the algorithm, all processes will reset their number I to 0. After this wait is ended, we will proceed like the bakery algorithm, but we will not increment the value obtained from the function maximum. When we obtain the value, we will check if it is greater than or equal to m. We will reset the number and choosing, and we will return to L1. This means that there is a possibility of overflow in the system, therefore we need to wait. Otherwise, we will increment the value, and the rest is exactly like the bakery algorithm. As you can see, we have not made significant changes to the bakery algorithm. The reason we are checking that if the number obtained by maximum function is larger than or equal to m is because of the fact that in bakery algorithm, a read operation that overlaps a write operation may return an arbitrary value, and this arbitrary value may be larger than m. So we have to check for it. In terms of performance and practicality, Bakery++ does not introduce new variables, so the spatial complexities of both algorithms, Bakery and Bakery++, are identical. The temporal complexity of Bakery++ depends on the number of executions of the goto statement exactly after label L1. This means that it all depends on how long it takes for a process owning a variable number I larger than m to reset its value to 0, and how long it takes for other processes to read a value for that register that is less than m. The reason Bakery++ is useful in practice is that it is almost as simple as the original bakery without new variables and fancy operations or functions. And there are no practical limitations for implementing the Bakery++ algorithm. This is because the algorithm is quite general and abstract, and for example, its variables can be emulated using files or any other means for storing information in a secondary storage in computer systems. Meaning that having different levels of cache or having multi-core computers does not limit the implementation of bakery algorithm. In terms of correctness, the Bakery++ algorithm does not introduce any new variables, and its control flow is almost identical to bakery. The changes that have been made to bakery include introducing a constant that represents the maximum value storable in a register. This is the constant m. As you can see, this has no way of affecting the correctness of the bakery algorithm. We have added a conditional statement and a goto after label L1 that does not manipulate the values of bakery's data objects. So this also has no way of affecting the correctness of the bakery algorithm. We have added the conditional statement before incrementing the maximum value obtained from reading all processes variable number. This is the value returned by the maximum function, and we have added the conditional statement. So again, it has no way of affecting the correctness of the algorithm. If there is a possibility of overflow in process I, then we simply set number I equal to choosing I equal to 0, meaning that we have reset everything and then we jump to label L1. Otherwise, we will continue by incrementing the maximum value and the original bakery algorithm itself. Again, everything is proceeding like the original bakery algorithm, and therefore its correctness is maintained. There are two questions about the Bakery++ algorithm. The first one is that what happens if there are more customers in the bakery than the maximum number that can be stored in a register? For example, imagine the system has too many users, more than the maximum value storable in a register. What happens then? One solution may be to use multiple registers for storing the value of number, and that is fine because bakery algorithm and the Bakery++ algorithm do not assume atomic read and writes of the registers. This may be one simple solution for this question. The second question is that what is the definition of the exact moment when a process is considered to have taken its turn for entering its critical section? Meaning that when is the process considered to have taken its ticket? One simple definition may be after incrementing the value obtained from the maximum function. This is actually a subjective question, and it should be considered in future works. We revisited the problem of mutual exclusion and the bakery algorithm, and we tried to solve the problem of integer overflow. Previous approaches to solving the problem of register overflow concentrated on making use of new variables and redefining the operations or functions used in the original bakery, and they were complicated solutions. Our solution, Bakery++, is unlike any other solution for this problem. It is simple, and it does not use additional variables, or it does not redefine the operations or functions in the original bakery algorithm. Again, Bakery++ is quite simple, and it differs from bakery in just a few instructions. We have specified Bakery++ in the Pascal algorithm language, and we have performed model checking using the TLC model checker to confirm the correctness of the algorithm. Thank you so much.